introduce you Dahlia Malkhi. She's a researcher in VMware research. Previously, she worked with Microsoft research in Silicon Valley. And after Microsoft closed the facility in Silicon Valley, she moved to Hebrew University. She is specialist in theoretical and applied distributed computing, and today she will present a small part of his work on Byzantine fault tolerance. You have the floor.
Yeah, thank you. Okay, super excited to be here. Less excited about having to stand here, but I'll try. So today, I'm going to talk about the classic foundations for Byzantine fault tolerance. So to those of you who are experts in the field, I'm going to remind what the classical way of getting decentralized trust is. To those of you who are not in the field, maybe I'll teach you a little bit about the classical foundations, and then I'll immediately ask you to forget what you know or unlearn what I'll teach you, and describe this exciting new approach, which we call flexible Byzantine fault tolerance, that changes the way we can build decentralized trust environments in two fundamental ways: flexibility and democracy. So flexibility means you can break and circumvent all the known resilience bounds, all the thresholds that are known in the classical foundations, without violating any impossibility result. And democracy means that actually the way you think about the system and what consistency is completely subjective. It's not determined by the system, it's determined by the observer, by the client. Okay, so let's get straight to it. So why are we looking at this? We're looking at this here today in tokenomics because the key core enabling technology for cryptocurrencies consists of this mechanism, of this engine that allows you to do a collaborative bookkeeping of a history of updates like payments or any arbitrary program. This is the core technology that underlies blockchain. And this is putting aside the key application that started this field, which is currency. So it's completely orthogonal and independent and not about the currency aspect. It's just a technology for organizations to share information and collaborate over decisions. In 2014, Mark Andreessen, who is the founder of Mosaic and is considered a thought leader in the Silicon Valley, he wrote an article in the New York Times about Bitcoin, where he said Bitcoin solved the Byzantine generals' problem. I was really happy to see this article. This is the first time that I saw the Byzantine generals' problem appear in the article of the New York Times. I've been doing this for, work in this field for over 2 decades, but this is the first time that I see Byzantine fault tolerance or the Byzantine in the New York Times. By the way, I started when I was 3 years old, when I say that I... So, it seems like, okay, problem is solved, right? Bitcoin already solved this problem. But when you look at the solution, actually, there are a lot of problems with the way Bitcoin solves the Byzantine generals' problem. So, there's energy waste. There are a lot of attacks that people described yesterday, mining attacks, parasite attacks, this, that. There are a lot of variations. There's throughput problems. But fundamentally, perhaps one of the biggest problems is that once you actually succeed in forming a proof-of-work-based solution to the consensus problem, you're a victim of your own success, and it becomes very sensitive and very vulnerable to centralization attacks or centralization problem. And this is a screenshot of a website called arewedecentralizedyet.com. How many people have seen this site before? Very, very few. Good, so you can go online on your phones right now. This is a screenshot for about a week ago, arewedecentralized.com. It actually tries to track various statistics about the decentralization of, the top 100 or so coins. And here's the top coins. The column that I highlighted says the number of entities in control of over 50% of the mining power of this coin. And you can see, even in this small font, that the top coins, Ethereum, Bitcoins, Stellar, Ripple, have, Bitcoin has 4 entities that seem to be in control of more than 50% of the power. Stellar, 1 entity controls more than 50% of the power. And all of them, none of them has more than a handful. So you start with this permissionless, super decentralized, super scalable technology, and you end up with a handful of participants in control of it. So that doesn't seem to be a good solution. So to really decentralize trust and to really bring organizations to share information and reduce the barriers for organizations to interact in a trustless settings, we feel that you need to go back to the foundations and look at how the classical solutions address this problem. So the classical foundations go back to an approach called state machine replication that essentially says at the basis you need to build a consensus mechanism among a group of known members such that you don't trust any individual member, but you trust the group as a whole to not have too many corrupt members, some threshold of them. And this basis of forming consensus allows you to form agreement on something like a database log, a history of updates to the information that they share. On top of it, you can build arbitrary state machines. Any state that you can apply the updates to can be coded this way. It's completely universal. Any algorithm, any functionality, any logic can be expressed as a state machine, so you can build your favorite application on top of it. Now, of course, if you went to the financial world, to the fintech, and told them, I have a great scalable solution for state machine replication, you will have a very short discussion with them. So you have to use, the terminology that they know. So you don't talk about a database commit log or a consensus engine. You tell them, I have a distributed ledger technology. Then they listen to you. And then, your state machine is really your persistence layer. And you're not talking about application. You're talking about a smart contract. And now you can have a dialogue. But fundamentally, the key challenge and the key enabler is the fact that this hierarchy, this 3-layer technology is decentralized, it's distributed, it's running among participants. All of them, each one of them has a copy of this rectangle hierarchy. And some of them might be corrupt, but they're running this distributed protocol that allows them to replicate this state machine. So again, in the blockchain world, you can think of it as a blockchain. This is the log of updates. Here, every log entry is pictured as a rectangle, so you can think of it as a block. And in the classical setting, what you have are n members. This is the group of known members that were admitted to the system, and some threshold of them, f, are vulnerable to an attack. They might just crash. They might be slow or suspended, or they might be vulnerable to a bug or a real, intentional malicious attack. So they are modeled as a fraction of Byzantine faulty participants. And they're running this consensus algorithm to form agreement on a chain, on a sequence of decisions. And if you can solve this problem of agreeing on one element in this chain, you can solve the problem for the entire chain. So what we concentrate on is a single instance of solving this problem among a group of replicas that have this responsibility to agree on what is this block or what is this log entry. And again, the model is the classical model where we know who is participating, We know who they are. They're admitted to the system by permission, but they simply don't want any single one of them to be trusted, only the group. Now, I said that we have decades of research and hundreds of publications in this arena. We also have academic and not just academic, serious industrial efforts to build common platforms that the community can trust. So how did that work so far? So unfortunately, the situation of this arena is pretty grim. One by one, both academic systems and industrial attempts to produce a platform that the community can trust have collapsed. So one by one, companies, very serious companies, IBM, Microsoft, they're with, JPMC, JP Morgan Chase, are withdrawing their attempts to build a platform because of serious flaws, not just simple bugs. My favorite one is this paper. About a year and a half ago, we looked at the most advanced foundation for Byzantine fault tolerance in a practical setting in the academic literature. This is a work called Ziziva. And the reason it's called Ziziva was they chose the last name, the last word in the English dictionary, saying we are the last word in Byzantine fault tolerance. This was very humble of them. And we looked at that work, and within 10 steps, consistency and safety completely breaks in this work. It doesn't take more than 2 leader rotations to completely break this work. So great. So that means there's still work to be done. And experts in the field have actually been tremendously busy in the last 3-4 years, just going through all the white papers and all the startups. They put out a solution out there and say, we have something new, we have something more scalable, we have something better than everybody else. Just understanding what is the core algorithm and whether it is known or really something new and which ones are similar to each other, just these are full-time job for experts. So let's go back to the classic foundations and give kind of a 5 minutes 101 crash course in this. So the fundamental decision that a designer of a BFT, Byzantine fault tolerant algorithm, faces, the first question they have to ask themselves is, what is the model of the system that they want to achieve in order to know what guarantees they can provide? So the first thing is you don't want to try to do something that's impossible, and you really want to know what is the guarantee against which attacks. And the first question you'll ask yourself is the solution and is the design you're building, is it going to be resilient against asynchronous networks, or does it require synchrony in order to guarantee consistency? So let me put this in more concrete terms. Bitcoin, Ethereum, all these Nakamoto consensus systems rely on synchrony to guarantee the consistency, the agreement. If the network is asynchronous, if it takes more time than the system is designed for the messages to arrive, there is no guarantee of agreement. There could be forks that are not reconciled. Okay, so there's a fundamental synchrony assumption. I'm not saying it's good or bad. You can, for example, assume that all messages will arrive in 100 years, and that might be a pretty conservative assumption that most probably will hold. Even if it doesn't, you don't really care, because in 100 years, we don't even know if the system will exist. So it's probably a sound assumption. So, but safety will depend on that assumption. If you don't want to assume that, then the network is asynchronous. You don't know for sure, and you don't want to rely on the network synchrony to guarantee safety. So these are the two main design, options that you have as a designer. And there are very, very well-known bounds and impossibility results that go with these assumptions. If you're in the asynchronous, the left side of the fork here, setting, you can guarantee safety only against a third of the system being corrupt. So that's a known impossibility result, and there's no way to get resilience to a higher threshold level. You can get solutions in this model. And liveness will be guaranteed by various mechanisms, despite the fact that you don't have a known bound on the synchrony of the network. But you can never get resilience to more than a third of the system being corrupt. If you want to get more, resilience to more than a third, then you need to make synchrony assumptions, and even then, you have a strong bound of a half. You cannot tolerate more than half of the network. So I'll give you a little bit of insight on where these bounds come from in a minute, but these are very well-known, the first foundations that you need to be aware of in this field. So again, by a show of hand, who learned something about BFT fault tolerance from this slide that they didn't know 5 minutes ago? Good, so it's, it's more than my first question, so almost like a third. And assuming you're not all Byzantine, already this is really important to know. So, even if you lose me in the rest of the talks, you see so many papers out there, so many startups that actually tell you that they solved the consensus problem with up to half resilience, and they don't assume synchrony, or things that are, just break these very, very known classical foundations. Okay, so I told you I'll teach you or remind you the classical foundations, and then I'll unteach you or ask you to unlearn them. So this is what I'm going to do next. So this is the design and known foundations until now. And essentially what they say is the responsibility of the system designer is to build a solution based on the assumption that the system designer makes, and then they can tell you what the system guarantees. So what happens if those assumptions don't hold? So for example, if more than a third of your network is indeed being compromised, what happens in the asynchronous world? Well, the solution completely collapses. What happens if your synchrony bounds are broken? Well, then the solution you built for the synchronous settings completely collapses. There's nothing left, no liveness, no safety, nothing. The solution is just gone. So this is where we come in with flexible BFT. And so I'll give you a spoiler on what you'll be able to do with flexible BFT. Well, you'll still have some assumptions and some bounds, but they'll be much, much better. So in particular, with flexible BFT, we will be able to tolerate 2/3 corruptions in the asynchronous settings, and the same thing in the synchronous settings. Okay, so I just told you this is impossible, but this is what we will be able to achieve. So how are we going to do this? We're going to, the solution approach I'll introduce has two fundamental components, flexibility and democracy. So flexibility will allow us to not violate, okay, not break, but circumvent the threshold bounds, both in the synchronous and the asynchronous case. And democracy will actually allow us to construct the same solution that will work for different assumptions. So you'll construct one system that then the clients, and clients here are abstractions for whoever makes decisions about the systems, whoever draw conclusions about the systems, they will draw their own conclusions by looking at the system without the designer determining for them. So you'll get a certain separation between the mechanism design and the conclusions drawn from the system. So why are we able to circumvent these impossibilities, these classical foundations? Well, what happens with these classical foundations is that they build a solution, and then that's it, it's rigid. But in runtime, there might actually be evidence that gives you information about what's going on in the system. In particular, the system might be running, and you actually witness that some participants are behaving badly. You can actually see that they're sending, equivocating messages. They're sending two messages, two different messages in a round, and they're not allowed to do that. Or you can actually see that a forking has happened, an inconsistent decision has happened. And again, in the classical settings, there's nothing you can do about it. You see that it's happening, you have this information, and you throw your hands in the air and say, there's nothing I can do it. The solution doesn't allow me to do anything. But based on this evidence, when you actually see and witness bad behavior, you allow to break the barriers on the thresholds of corruptions, because you can say, yeah, I can see some corruptions, I can see how they are behaving, so they're not arbitrary anymore. I can see exactly how they behaved. I can make some assumptions about the rest of the system and about how they behave that allow me to increase the corruption level. And in particular, when you see this behavior, in order to not make this too abstract, one thing you know about these participants is that they are not crushed. You actually get messages from them, and you can see that they're trying to cheat. So in particular, it's okay to wait for other messages, because these faulty participants that you see and witness their bad behavior, they're not crashed. They're available, they're responsive. So this will allow you to obtain a higher resilience than, for corruption than the original bound. Now let's get to the democracy part of it. Why would you want democracy, and why would you use democracy? Well, so in the classical way of designing solutions, all the transactions, all the blocks in a blockchain are equal. But in reality, you might have transactions that are much higher stakes. So you might have transactions in a blockchain that are buying coffee for $5, €5. And you might have other transactions that are buying and selling a house for €1 million. You don't want to treat both of these transactions with the same care and the same caution. You might want to be much, much more prudent and much more paranoid about the €1 million transaction than the coffee transaction. Or there just may be different abstract clients of the system. There might be an auditor on behalf of a government that has very strict beliefs and guarantees that it needs to hold about the system. And then, there are other users that have very different beliefs. So this is why you want a solution that allows the clients to draw the conclusions about commits and transactions, rather than the system deciding for itself. So I'll start with flexibility and talk about what we can do. So first of all, what is the fundamental difficulty here? So reaching consensus is very easy if you don't have faults. Just wait for everybody to form agreement, and this is resilient to everybody. In particular, everybody's waiting for me to participate in the decision, and they cannot forge my messages. So I know that whatever I see, and when I see everybody agreeing to it, that's a safe decision. That's very trivial. The problem is that it's not very live. If you wait for everybody to participate in the decision, then even a single member that is slow or crashed or detached or malicious can prevent progress. So there's a fundamental tension here between fault tolerance and ease. So if you look at solutions without giving a specific protocol or getting into the details, the key components of any solution to the consistent problem will be something that in the literature is called a commit-adopt core. Essentially what it says is there will be a group that participates in certifying a commit decision. Somehow, I'm not getting to any specific protocol, but there's got to be a group which is really not the entire system, otherwise we don't have fault tolerance. There's going to be some group that we call a quorum, that will be enough to somehow form a commit decision. And what you need to guarantee is that if this is possibly a committed decision, then this quorum is able to cause the remainder of the system, even if it didn't participate, to adopt that decision. Yes?
So I'm one of those who don't know anything.
Yep.
Is that classical, what you described? You told us you wanted us to unlearn, but this sounds familiar to me.
Yeah, no, that's...
That already exists.
Yeah, so this is a core of any solution, I'm trying to really abstract it without giving a protocol in a talk. This is a core principle in designing agreement solution, fault-tolerant agreement solution. There's got to be a subset, we call it a quorum, participating in the decision. But then, moving on to the system, you have to guarantee the safety of the decision by adopting what this core did and passing it onward. Okay, so this is the classical difficulty. So let's look at what is the size of the score that will be needed in order to provide both safety and liveness. So for the first decision, in order for this quorum of size Q to be able to reach a decision, again, without thinking of any specific protocol, just we have a group of banks, a group of N participants, and Q of them need to be able to form a decision, while the others may be offline or faulty, okay? So obviously, we need at most 1 minus Q to be faulty. Otherwise, there's no hope of collecting participation from the remaining Q. So if Q is the size of this quorum, 1 minus Q is a bound on the fault tolerance for liveness. This is not very deep math. Did I lose anybody? Raise your hand if I lost you. Okay, good. So this is liveness. But if we allow Q to be the ones who have this authority to participate, then that means that later we also continue to the next decision and continue the chain of decisions with just Q participants. But now we need both of these Qs to intersect and intersect in an honest, a non-corrupt participant. So a not very difficult computation is to see that if the first Q and the second Q that are potentially two different sets, I don't have control over it, it's a distributed system, if they need to intersect in at least one correct, one non-corrupt member, then at most 2Q minus 1 could be faulty. So for what we get is for safety, we have a bound on resilience, which is 2Q minus 1. And for liveness, it's 1 minus Q. So what we get is the Byzantine resilience, the resilience to faulty, is upper bounded by both of them. And obviously, the optimum point would be if they are the same. Okay, so just again to see that we have deep mathematicians who can solve this equation. What is Q under these conditions? Oh, come on, don't be shy, shout. All right, so we had some people who can run oracles and auctions and see where this converges to. Can somebody, be brave and say with confidence what they think Q is? What? Okay, I think the majority is converging to the right answer. Yeah, so Q, the optimum Q, well known in the literature, is 2/3, which means that the resilience, okay, the threshold, the upper bound on resilience in this strawman situation would be 1/3. Okay, so that's the core difficulty that we had until now. Why can we do something better? So the whole point is that we're going to favor safety over liveness in situations where we have evidence that some of the members are participating. So what we're going to say is we already have liveness, right? The bound 1 minus Q was in order to guarantee that we get enough responses. But if we get responses from some of the participants, but they may be bad responses, or we don't know if they're bad or not, but we get enough responses, we can actually get higher safety threshold. So we can expect higher Q, not compromise liveness, and definitely get safety. So this allows us to get higher Qs by introducing this new concept, new type of failures, new failure model, which we call active but corrupt, or in short, ABC. Okay, so what are ABC faults? ABC faults participate in the protocol. They respond to you. It's okay to wait for them to return responses to participate in the protocol. They're not going to hurt your liveness. Why? Because they don't get anything. They not gain anything. They're not going to be able to break safety. They're not going to be able to double spend or get any benefit, any utility by slowing down the system. The only benefit, the only utility they get is by trying to be corrupt. So I'm not going to hurt liveness by waiting for more responses from them, and I can get higher safety. So how much higher? I can get 1 minus Q Byzantine resilience, an additional 3Q minus 2 ABC resilience. So this is what you get as a result of applying this ABC model. So far, I kind of gave a high-level intuition on the bounds that you would get in an asynchronous setting, and a very similar, slightly different, but a similar way of thinking gets you to these bounds in the synchronous setting. Let me make this a little bit more specific and just use numbers, even though these formulas are, as you can see, not very deep math. So, if the Byzantine threshold in the asynchronous case is 1/3, if we don't know anything, and we really still want to tolerate 1/3 Byzantine failures, there's nothing really we can do. No ABC faults, and we get to the classical bound of 1/3. But if we know that all the participants are active, and it's okay to wait for messages from them, and the only thing they're going to do is try to actively break consistency in the system. They actively want to double spend or get some utility from the system, then all of the faults are not Byzantine. They're all ABC faults. And then something really interesting happens. We can tolerate 2/3 ABC faults, not 1/3. And the overall tolerance is going to be 2/3. And, all the points in between are also possible. Maybe we can't get the participation of 1/4 of the network. Maybe they're just crashed, or maybe they're Byzantine and trying to really prevent the system from working. Then we can tolerate additional 6 ABC faults. And again, the overall total resilience will be more than 1/3. Or, we can move closer and closer to 0 here, and then tolerate more and more ABC faults, and get, closer and closer to 2/3. And 2/3 will be the maximum here. In a second. And I just want to say, just finish the sentence, sort of the same situation with slightly different math holds in the synchronous setting, allows us to always be resilient to 2/3 corruption. Yes, now you get to ask your question.
It's a bit difficult to understand this beautiful picture if one does not know what ABC is. I know you already explained, but
yep.
I did not understand. Would you mind explaining again what ABC is?
Yeah, I don't mind explaining it. I have 28 minutes, any number of times, and it will repeat a little bit. But again, I don't know if I need to go back to the slides. Again, the idea is that in classical settings, we assume a threshold of Byzantine failures, and Byzantine failures are arbitrary. We don't know anything about their behavior. In a true running system, you could see that the behavior of some participants is not arbitrary. You can actually see that some participants are behaving badly. They're sending corrupt messages. They're sending 2 messages. You can see evidence that, consistency is broken. Or even if you cannot see, you can hope that this is the case. And you may have, some game theorists in the audience that later will analyze the incentives for participants not to break the system by slowing it down and not being able to commit any transactions because they don't get any utility from it. The only way they're going to attack the system is by trying to double spend. These are not Byzantine failures. These are active but corrupt failures. They're corrupt. They're going to try to get utility out of the system. They're going to try to game the system. They're not obeying their protocol, but they're not Byzantine. And that's the point of this new model. It seems like a trivial observation, so maybe that's your difficulty. It is trivial, Okay, but nobody has made it before, so everything is trivial after you make this observation. These are not Byzantine failures. Okay, these are different types of failures. We call them ABC because we make a strong assumption that the way they're attacking the system is by being active, but not following the protocol. What that means is, remember my seesaw picture, it allows us to break from this tension between liveness and safety. Because for liveness, we had to assume that all of these faulty participants might never respond. We cannot wait for their responses. But ABC is a weaker assumption, or if you like, a weaker assumption about the threat or the attacker. It assumes that the attacker will respond. We can wait for messages from these faulty participants. Yep.
What does it mean that they are active? Do you assume that they will not crash within
Yes.
a bunch of rounds?
Yeah. They will not crash, they'll respond. That's
They
it.
may crash.
Yeah. So these are weaker type of faults. They're not the strongest type of assumptions. They're not Byzantine. And I would say that when you have a consortium of 400 banks that are building a blockchain as the foundations of fintech, assuming that the banks will participate in the protocol, not crash, some fraction of them, maybe not all of them, assuming that they will actually be active, is a pretty reasonable assumption. But you don't want to trust their honesty. They're trying to game the system. They're trying to get utility.
It's a dangerous slope, right? Because if I know you're doing an ABC thing, then I can kind of be a little, I can start to look in a certain way to you. You're going to assume I'm active.
And you might stop the system from making progress. Is there any gain from you? Any benefit? No. You're going to prevent all of us from making progress. That's fine.
It depends. You have not told us what is the objective they're trying to maximize.
I'm trying to solve consensus with a higher resilience to corruption.
But if you say they have an objective, but I don't say what objective it is, how is that different from saying I don't know what they do?
So the difference is I do say they have an objective. And again, I believe there's a game theoretic analysis that can show that they don't get any benefit if they cannot break the safety in any behavior. They cannot break safety. They don't get fees, they don't get transactions committed by not participating. So the rational thing for them to do is to participate, and I believe you can formalize this and find an equilibrium. This is their rational behavior, but this is an assumption. So you don't like this assumption, that's fine. I didn't like the assumption that says only a third are faulty. Okay, both of these are assumptions. If they're broken, the system has no guarantees. It's kind of like you go to a computer store and you buy, remember we used to buy boxes with CD-ROMs and software in it, and on the back of the box, it said what are the conditions under which the system works. And you can like it or not like it, but these are the conditions. These are the requirements for the system to work, right? So you like your system to work with the assumption that at most a third are vulnerable to corruption, and 2/3 are honest. That's fine, you go and build your system that way, and I will bank, I will deposit my savings in this other consortium that says up to 2/3 can be corrupt. But the system will not make progress if, for some reason, they're behaving irrationally and they all kind of stop responding. And let's see which bank makes more money at the end of the day. Yes, Peter.
Just to understand, this ABC model, does it include the behavior of fault, the classical one, where you try to make the system appear partitioned? So you tell one
Correct.
information to one quorum and the other information to the other.
Oh, no, it does include this. The only thing it doesn't, so it definitely corrupt deviation from the arbitrary deviation from the protocol, but the only thing it says is you decided that it's okay to wait for responses. That's all it does in a classical setting. So you build your protocol, you always build your asynchronous protocol or even synchronous protocols, you build them by waiting for a quorum of votes or messages to arrive. Okay, if those messages don't arrive, you cannot make progress, always. Even in the synchronous setting, you don't just wait for the bound, you wait for 1/2 + 1 votes to arrive. So you will wait for more votes, that's all it says. And
This is the classical counterexample to show that you need
Yeah, and like I said, we're not violating any possibility results here. Okay, what can you do with flexible Byzantine fault tolerance? So far I showed only the flexibility part, not the democracy, taking a little longer than planned, but that's okay. So what can you do with the flexibility? Well, you can do some pretty amazing things. So in the asynchronous model, for example, when you observe ABC behavior, okay, so you observe participants are responding to you more than your bound would otherwise assume. So let's say P have already responded and are active, and you think that they might be corrupt. This is your assumption. They already responded to you. Then what you can do is you can say, okay, P have responded and they're ABCs, they're not Byzantine. Therefore, my threshold assumption on who is Byzantine is a third minus P. Because the P, I know that they're ABCs, okay? But what happens is that you don't get a third overall fault. P plus third minus P is a third. So you don't get that the sum of the ABCs and the Byzantine is a third. What you get is that a third plus P could be corrupt. Okay, so this is the magic. So you have P that are ABCs, a third minus P that are Byzantine, and something is wrong with the math here, right? A third plus P could be a total of corrupt. So this is what you can do with flexibility. Let me quickly zoom through some of the democracy part. So here, okay, so let me say what you can do with the democracy part first, and then I'll zoom through, an example of how you can do it. But the what is probably more important. So the democracy part goes even further. It says the same solution can now be interpreted in a different ways by the client role, by the actor that we call the client. So what that means is that there are active replicas implementing your system. These are the banks. And then there are the clients that decide if something is committed or not. So what you could do with this democratic way of building the design is separate what the solution was designed for and how the system is used. And in particular, without changing the system, that's, hard fork or upgrading the software completely or rewriting the entire system, or reconfiguring, without doing any of these things, if you see that the system corruption level approaches 1/3, you can switch, for example, from asynchronous to synchronous mode in the same solution. This is under synchronous mode. In the synchronous mode, you could do the opposite. If you see that the communication in the system is approaching the bound that you seem to think is dangerous, you could switch back to asynchronous mode with the same solution, without reconfiguration, without relying on consensus itself to help you. The same system can just be observed differently. If you see that your assumption has been wrong and actually two conflicting decisions have been committed, in the blockchain world it would be called forking. Normally, in the classical settings, there's nothing you can do. You have two committed decisions, both of them look alike, and there's no way to determine between them. What you can do with democracy is go back and change your assumptions on the same run, on the same transcript, and one of the decisions will be favored. You could also have these higher paranoid models applied only once in a while. So you could get safe checkpoints of the system every once in a while by adopting higher level assumptions, let's say every hour. And like I said, you can also distinguish between high stake transactions and low. And again, the same system, the same implementation, you could wait for longer, higher assurance on high stake transactions. Let's see. So I wanted to tell you a little bit about how we get democracy in the synchronous setting. I'll do it very quickly. I might lose some of you for the next 10 minutes, and then I'll wrap up and maybe get you back. So very quickly, I wanted to introduce a protocol for the synchronous setting, which is democratic. And I'm very excited about this protocol, even if you could forget about the whole ABC model, just by the protocol itself. So first of all, it's an extremely simple protocol. It's in some sense the simplest BFT protocol by itself. And the way it works is kind of the textbook way you would think that a synchronous BFT protocol should work, except that this is not what you get in the textbooks. So how does this protocol work? So in this protocol works by rotating a leader, like most solutions in this area. The leader will broadcast a proposal. Every replica, when it hears the proposal, will vote for it by broadcasting a vote, and the vote also serves as being a reproposal. So everybody that didn't get the proposal originally from the leader and gets the broadcast of a vote will also see this proposal. And then everybody waits to collect votes from queue, this quorum queue of participants. And this is called a queue cert, a certificate on the proposal. And as soon as anybody collects a queue cert, the clients observing the system, getting any information from this system, any broadcast from the system, not the replicas themselves, they wait to delta to consider the decision committed. Okay, so notice this protocol is synchronous. It relies on synchrony for safety, but the replicas never used any time bounds, never waited delta. There's nothing in this protocol that is synchronous. Only the commit decision is delayed to delta, and that makes it completely democratic. I can decide when something is committed completely differently from Peter there, who is frowning and not trusting that this protocol is correct. Okay, now I already said at the very beginning that the key difficulty, the key challenge, and the key thing that consensus protocol need to solve is commit adopt. So I showed you commit, but without adopt, without being able to address a leader change, I haven't done anything. I might just as well say, let's wait for the leader and decide on the leader. So the whole difficulty, the core difficulty is building a fault-tolerant solution that rotates to the leader. The reason I'm saying this is that half of the white papers out there of blockchain startups that we see say, yeah, we solved this problem, and they never tell you, anything fault-tolerant. But in this case, the new leader has a very, very simple protocol, and again, it doesn't use synchrony. All it does is waits when it starts to collect the latest certificate from queue replicas. And it's very easy to see why this protocol is safe. I don't have time to get into it, but if you sit for 2 minutes, you can see that if any replica commits to a queue certificate, then no other replica could have even voted for any conflicting certificate. It's very clear to see that this protocol is live because it's only waiting ever for queue to participate, whatever queue is. And it's democratic. It doesn't use delta anywhere except in the commit conclusion by delaying the commit conclusion at the end. So that means that this client actor is free to use whatever delta she believes in. Every client can use a different delta. And it's got flexibility. So in particular, this queue can be larger than a half. So if you believe that some of the replicas are ABCs, they're active but corrupt, you can set your queue threshold to be higher than a half. And by waiting for more votes, you get resilience to queue failures. So this is what you get in the end. Let me skip. So this is the same protocol by pictures, in case the verbal description was too fast. And this is what you get in terms of resilience bounds in this protocol for the synchronous setting. So for the synchronous setting, ignore the R here, which is another parameter we can introduce. What you get is that the Byzantine threshold would be y minus q. Again, these are the ones that we really cannot rely on their participation. The ABC threshold is an additional 2q minus 1. And so the overall resilience is to q. So all the replicas in the certificate minus 1 can be faulty. So in particular, you always get that if you choose Q to be 2/3, you always get resilient to 2/3, no matter how many are Byzantine and how many are ABCs. To show this pictorially, what you essentially get is a range of possibilities for tolerating a combination, a mix of ABC faults and Byzantine faults. So in particular, for the synchronous setting, you can always get to 2/3 fault tolerance. So you have this green triangle that no matter how many Byzantine faults you experience in practice, you can always tolerate a threshold of 2/3 corruption. So there's really no reason to make any assumptions about Byzantine. For the asynchronous setting, this is this, I don't know, orange triangle. You get a trade-off. The more Byzantine faults you actually experience or you actually tolerate, the fewer ABC faults and the fewer overall number of corruptions you can tolerate. But if the actual number of Byzantine, remember those Byzantine participants are acting irrationally. They're just not participating in the protocol and they're not getting any benefit from it. If that fraction is actually less than 1/3, then you can grow your overall corruption resilience higher and higher. So this is for one particular choice of Q. Now you can actually change your choice of Q when you design the system, and these are the same graphs for different choices of Q when the system designer builds the system. So these red circles these are points for synchronous beliefs. And remember, in synchronous beliefs, the line was flat. It doesn't matter how many actual Byzantine faults occur, the resilience, the corruption resilience remains the same. So these are the points that you get for synchronous tolerance for different choices of Q. And these are the curves, the trade-offs between Byzantine and ABCs that you get for synchronous solutions. Kind of the same curve now with a few of the classical results that we know about depicted as a single point. So what we get is a range where the designer and the client can choose their assumption level. All the classical literature is represented as single points here. Okay, so these are asynchronous solutions, these are synchronous solutions. They're presented as single points. And even their optimistic version. So some of these solutions have optimistic versions that are presented here as diamond. In particular, the Ziziva solution, that was their main contribution, is to introduce an optimistic track. Well, there's also a safety violation, but regardless of that, their resilience in terms of Byzantine threshold did not go high, even in optimistic setting where everybody responded. Okay? And in our case, in this setting, we would go as high as 2/3. So to wrap up, I've introduced flexible Byzantine fault tolerance. It's a new approach for separating the design of the solution from the beliefs and the fault model in such a way that, first of all, it allows us to circumvent, not violate, not break, but circumvent all of the impossibility threshold bounds. The ABC faults are tolerated in addition to Byzantine faults, not in place of them. The synchronous version is itself a new protocol that doesn't assume synchrony. So even the synchrony bound, this delta bound, is itself something that the clients observe and not the system designed for. And in case of the asynchronous setting, it's pretty surprising that you can tolerate up to 2/3 corruption faults. I just wanted to say this is a new approach. It bears some similarity, not really analogous, but some similarity to the way we think about Bitcoin or Nakamoto consensus. So in Nakamoto consensus, we also have this phenomenon where the system is running, and what we consider committed is up to us, is up to the observers. And in particular, we consider a block committed in Nakamoto consensus when it's buried certain number of levels deep in the chain. Now, this is the observer's belief. It doesn't change the protocol. The same protocol runs, but the observer may believe that a block is committed after being 3 levels deep, 6 levels deep. You can even change these beliefs for different types of blocks. If they have high stake transactions, you can wait until they're buried deeper level. So there's some degree in which this notion is already familiar to cryptocurrency enthusiasts. And this is a very different way of taking this into the traditional setting. But unlike Nakamoto consensus, it actually changes your resilience to corruption level. Whereas Bitcoin, you can just wait more time to believe that something is committed or not, but you cannot change the fundamental resilience to asynchrony attacks, which Bitcoin is not. You cannot change the fundamental resilience to only half of the network being corrupt, which is needed. So I guess I'll stop here and take any questions. I had a couple more slides. Thank you. If you don't ask questions, I have some marketing slides for my company. But,
I have a question to you. Not that I wouldn't like to be exposed to the marketing, but before maybe. So I have a question about this double broadcast thing that you shown two-thirds in the talk.
yes?
So at some point you said...
The synchronous protocol, the simplest synchronous
simplest
protocol.
one, yeah, because this is the one I understand somewhat.
Yeah.
So, there's a constant somewhere which is Q, and this is the number of doubly broadcast messages that I'm waiting for as an honest participant to make some kind of decision, correct? Mm-hmm. And so somehow your magical flexibility comes from the fact that I'm going to observe the other nodes. So concretely, maybe I see that a node among my colleagues has actually sent me 2 messages that are different, for instance. Or, for instance, that's part of my question actually. What is it that makes you, what is it that will lead me to conclude that, oh, this is an ABC node, and what do I do with the queue then? I increase the queue a little bit.
So let me, so I didn't have time, but let me show you the picture anyway. So first of all, this protocol is a new protocol that separates the commit decision and makes synchrony assumptions only commit, even in the classical setting. So forget about ABC fault. You're in a 2f+1 setting. You assume half can be Byzantine. This protocol already gives you democracy. Okay, so forget about flexibility. This protocol gives you democracy. It defers all uses of your synchrony bound, anything you assume or know about the bound on transmission delays in the network. The replicas don't use it. Only the commit decision, whoever looks at the system and decides when something is committed, use it. It's also the simplest protocol I can think of. It's, leader broadcasts, everybody votes, and you wait for, f+1. To vote on it. So I'm very excited about this protocol, even if you forget about all the flexibility. So this is, for example, this protocol in a classical 2f+1 setting. You have 7 replicas here, and up to 3 are Byzantine. No ABC corruptions, no detection of ABC corruption, and you just, collect these votes, rebroadcast them, and you get to a commit decision which the client actor gets to decide. Now, in addition to that, this is why it's safe. In addition to that, you could have a mix of faults. So if these presumed Byzantine replicas, so still having 7 replicas, but if some of these presumed Byzantine replicas are rational, and the way you observe that they're rational, you don't have to actually see 2 equivocating messages. You just wait for 2/3 votes in order to certify. You simply, you make this assumption, you make this bet that they're going to act rationally. If you lose your bet, we had this discussion before, your system might not make progress. And this guy's system, I don't know his name, will make progress. But if your bet is correct, you will make progress and your system will be safe when his system is attacked. So you, just like any fault model, you decide what you choose. If you choose to wait for 2/3 votes instead of half plus 1 vote, in this case, it would be 5 will take to 5 or 6, yeah, 5 would take to certify a proposal instead of 4 in his system or in the classical system. Yeah, well, I'm giving you credit, okay? I mean, you know, I come from the Silicon Valley. He has a company, I have a company. I'm trying to tell you that my product is better, right? So here you wait for 5 votes to certify the leader's proposal, then again wait to delta, which is completely democratic, it's not part of the protocol, and then you consider it committed. You'll definitely get safety against, you know, the Byzantine threshold that was given before. You will get liveness if it was the right assumption, if some of the corrupt replicas were acting rationally and trying to actively break the system. They cannot break your safety either way, and you're waiting for more votes to get this higher resilience to dishonest behavior. You don't have to actually detect the Byzantine behavior. Does that answer it? Yeah.
My name is Bruno.
Hi, Bruno. We're hiring, by the way. Do you want to ditch your startup because mine is better?
No, thank you very much for your wonderful, clear and pedagogic talk. It's great for us who don't know computer science. Thank you very much for doing that. So I use game theory. I'm an economist, and I use game theory, and in particular, I would like to use it to try to understand these things. And it seems, you will tell me if I'm wrong, it seems that, in a sense, in computer science, originally people just assumed some behavior for honest guys and saying the Byzantine are going to do crazy things. And then it's the opposite of what economists do, in which they say, we give people an objective, and they try to reach that objective, and that determines their behavior. In a sense, I think, I may be wrong, that your ABC players are, in a sense, in between the Byzantine, who are completely unspecified, and the game theoretical players, whose objective is completely specified. I think you're saying that you don't know exactly what their objective is, but you assume, you make a good assumption, a plausible assumption that their behavior, that their objective should imply, whatever their objective is, it should imply that certain things should be observed.
So, correct. It's a different model. You could think of it as in some sense, interim. I'm not the first one in the distributed computing world to consider game theoretic models for these protocols, and I can refer you to some papers if that's of interest to you. I think one of the first ones was this BAR, Byzantine altruistic rational model. Different, and there have been others. BAR did not assume a mix of these faults and did not, made some assumptions about the lack of collusion or weak collusion among the participants. Then there were some follow-on works that showed tolerance to colluding rational players. And the difference from this model is that we assume this mix which results from designing the protocol to be safe against truly Byzantine behavior. So by being truly Byzantine, you're not going to get any utility out of it. The other difference is that we didn't do the game theoretic analysis yet. So this is why we're calling them ABC and we're not calling them rational, because in order to call them rational, we have to prove it. And I'm hoping to continue this work, and I think there are a lot of interesting open questions that need to prove that this is really a rational behavior. So far, we did what everybody in the distributed literature does. We just made a different type of model. But I think there is a game theoretic analysis waiting to be done here, definitely. But yeah.
Thank you for the talk. Now, it's just an observation that when I understand that
really the problem that Nakamoto solves. For decentralization, you cannot fix N. And this is what you need, a proof of work to avoid civil attacks. And, you know, so, I mean, decentralization and a closed system is not compatible because someone decides who participates, right?
Yeah, you know, I showed this slide at the beginning. Are we decentralized yet? So we know what happens in these permissionless settings. They're not as permissionless. You start with permissionless setting, you end up with a handful of participants. Another model is stake, which is an indirect projection of the proof of work setting onto this model, onto this classical model. But then you end up, you know, still with the need to design solutions for this classical model. So you can think of it as a proof of stake model. I agree with you, permissionless solutions sound great. If anybody could come up with, you know, a solution that really fights the civil attacks without leading to centralization of power, I would be really interested in also building solutions for that model. For now, I don't see in any of the works out there.
I mean, I think the web page you show with the number of actors that control 50% of the hash rate, these are pools. I mean, pools are done by people that may change and happen in Bitcoin.
No, but in terms of the participation in the protocol, they only have one block. They're all working on.
When a pool becomes behaving properly, miners will change pools, right? So I mean, it's not just counting pools that is a measure of decentralization, I think. But anyway, this classical.
From their participation in the consensus protocol, I could take these pools and build a Byzantine fault-tolerant solution with 4 participants, and I would get the same.
Byzantine fault-tolerance, you're fixing N, right?
I'm sorry?
You're fixing N. You're talking about.
Yeah, 4 pools. That's N.
No, but I mean, everybody is free to.
It doesn't matter. The pools are participating as a single actor in the consensus protocol.
The thing is that the interesting question is to know what of this classical work on Byzantine general problem can be applied to an open setting, like the Nakamoto.
Yeah. So I have.
For an open network. I mean, this is what I'm asking. Is there any?
There is this system called Algorand. What they do is they elect a committee. Yeah. There is this Algorand by Silvio Micali. Essentially, what they do is they in every, I don't know if it's every round or every epoch, they elect a committee, which is they do it randomly with some essentially it's like a lot of lotteries. Proof of stake. They use some proof of stake lottery in which a committee is elected, and then they run Byzantine agreement in a known committee, so everybody knows everybody in the committee. And by the fact that this is a random lottery, the probability of having too many bad people in the committee is quite important. But
yeah, so I think there are many connections between the classical setting and the proof of work setting. I think Amar, over there. Amar in his keynote yesterday gave a pretty good survey of some of these connections. You could add to it finality gadgets like Casper, which take a group of stakeholders to finalize what is not being finalized and not trusted in the proof of work setting. It's kind of an interesting discussion to have. I think that in the enterprise setting, not the currency-related or cryptocurrency-related setting, what we see is that the industry is primarily interested in permissioned solutions. And I would argue that even in the cryptocurrency settings, Algorand, other solutions like Dfinity, many others, and Casper, even Ethereum itself, is moving to this classical setting because of the limitations of the proof of work setting. But they're different beliefs.
Business is not decentralized. I mean, you won't send an open source, anonymously written code, right? So this is full centralization comes from a development like in Bitcoin where it was developed by anonymous people. I mean, if there is a company or a foundation behind, it's not really decentralized, at least the development.
Yeah, well, we disagree.
Eventually can...
Any other questions?
there are other
Yeah,
questions?
there seem to be.
Yeah.
what ABC describes is what the adversary tries to do. So do you feel confident that, well, the system designer can find all possible behaviors that the ABC adversary might express, so as to be, to know what to expect? Because otherwise, what I get is that you could end up in like a cat and mouse game where the adversary might be ABC, but he might express some behavior that is not expected and is not observed by the client or the peer.
Yeah, this is a great question. Let me show my summary slide one more time. You understood very well, but I want to very, very much clarify that this model does not rely on detecting ABC behavior. If that wasn't clear, I really want to clarify it. Instead, the way you should think about it is you design your, this is a new way to design BFT solutions such that by omitting messages, you cannot break safety. And now it's your belief to determine whether the participants that you chose in your permissioned consortium, whether they will behave in a way that will sound irrational, pending, game theoretic proof, and will really not participate, or you believe that the participants you chose in a permission setting in your consortium, these big, credible, organizations, enterprises, banks, or whatever, whether the only way that you believe they might get corrupted by an attacker or by a bug is, not by omission, but by actually somehow deviating from the protocol. You've designed your protocol in such a way that they would not be able to break safety, and then you believe that therefore they will participate. But the safety and the design of the solution does not rely on detecting such a behavior. It allows you to switch your beliefs based on what you observe in the system, but at the end of the day, it's a belief. And this is what we do in, I think, in all systems. If we do our job well, we present to our customers a specification of the assumptions and the guarantees that the system provides. Okay, at least you can formally specify what is the assumption and what is the guarantee. You cannot force an assumption. It is an assumption, but at least you can articulate it. That's what you can hope for. Yep. Amar.
Very nice, because it breaks this dichotomy that we have been living in for a while of crash versus Byzantine.
Yes.
Now, it brings back to my mind some of the earlier works in the 80s maybe, and I think you might have been involved in it, involving omission failures.
Except that, let me interrupt you before you finish. Except that there has been hybrid models of crash in Byzantine. And this is in some sense the opposite. It's non-crash in Byzantine.
Yeah, no, I'm familiar with the hybrid. Yeah. No, I'm going back to the omission failure. And there was work on send omission, receive omission. You were involved in some things like this maybe. So was all this work in synchronous systems? Is there anything that was in asynchronous systems and kind of going in the spectrum?
So works on omission failures seem less relevant because they were actually a weakening of crash failures. And they said you're not binary crashed or non-crashed, you're occasionally omitting messages. I'm not familiar with any work that combined omission and Byzantine. There might be. But even if there were, I would assume that they combine, just like people have combined crash and Byzantine, they would combine omission and Byzantine. And again, this is in some sense non-omission. This is an assumption that you will not omit. Yeah. Do we have more time? I don't.
20.
All right. Last question before lunch.
Okay. So is that somehow related to some reasonable assumption that you could make about a bunch of banks, which is that they might want to cheat because maybe the chief has lost everything at the casino last night, but they don't want to be seen as cheating. so which we call covert adversaries in cryptography.
I think yes. I think it fundamentally goes to what you believe is in the interest of participants. I don't see why, I mean, they might truly crash, that happens. You might assume that the number of actual crashes of serious enterprise participants is pretty low. You know, systems today are pretty reliable and they're replicated internally and, you know, they're 24/7 available. So yeah, you might assume that in a consortium of 400 banks, 1/10 can crash, not 1/3. So then the question is, yeah, what do you assume is in their interest to try to do? So just avoiding to participate to prevent the system from working, that you know, doesn't seem like it serves any purpose for them.
Okay, let's type to the speaker.